So hello, this is Galen Pickett, this is a video that I'm creating in support of the Physics 151 Summer 2019 course. A student asked in the office hour last Wednesday if they could get a little more clarity on what happens when you arrange springs in parallel and in series, and why one winds up being a stiffer configuration for the springs and one winds up being a less stiff configuration for the spring. So I wanted to make a short screencast video along the lines of the ones I've already made that might help everyone in the class figure out what's going on with that. So here we've got two situations. We've got pictured here on the in the note screen a parallel configuration of springs. That's the top here. I've got two springs, and these are identical springs that are one by one being pulled in the same direction. They're sitting parallel to each other. The second configuration is a series configuration. So this is series in the sense of serial, one after another after another. And here we've got two springs that are arranged one and then the other with a junction in between where the two springs are connected. Either of those two configurations can be thought of as a single spring with a different effective spring constant, K effective. And the question here is that effective spring constant. So this would get the same response if I replace those two springs with a single spring with this effective spring constant. Can I figure out what is the stiffness of that combination by just thinking of it as a single spring? Now, if you have done electronics before, you maybe know that there are rules for combining resistors in series and in parallel, and those come from an application of actually the energy principle and the momentum principle, the same way we've been using them in this course. But doing circuit analysis, you know that you can chunk this set of resistors as a single resistor. You can chunk this couple of resistors as a single resistor, and that helps you figure out what's going on in an electronic system. Here, this is a mechanical system. The energy and the force is distributed between those two springs. How is it distributed? So let's take a look at the top case, the parallel case. That's the easier one to analyze. If I look at this junction here that I'm holding on to as my system, so the system has got three things that are attached to it. It's got two yellow springs and my force, which is pulling the two springs out. So let's specify these springs that I've pictured as having a spring constant K0. And when they're not being stretched by anything, the length of these springs is essentially 0. So the springs just snap right back to a very compact package. So another way to say that is we stretch the springs much farther than their at-rest configuration. So I'm going to ignore the fact that these springs actually have a distance, a manufactured length. It's essentially 0 for what I'm about to discuss. So if I take a look at this system for this parallel case, the system is this red dot. I got three things that are attached to the system, one force from my hand, and then two forces backwards. I'll call that F spring and then F spring. Notice I've drawn these two forces as I've added them together, tail to head, tail to head. So that is the net force, or the free body diagram, if that's the language that you're familiar with. Now, what I'm asking for this situation, I'm asking how far L is this system stretched in equilibrium when I apply a force capital F. So the fact that it's equilibrium means I can use the momentum principle. The final momentum of that junction is 0 because it's at rest, and the initial one is at rest as well. So I've got the change in momentum is equal to the final momentum minus the initial momentum, but those are both 0. 0 minus 0. So I've got the momentum didn't change. That's one kind of equilibrium. The thing is just standing still. Another kind of equilibrium would be that the object is moving with a constant velocity. That's not the case here. Now that should be equal to the net force times however how much time I'm willing to hold that object in equilibrium. So I've got, let's call this the x direction. X hat goes that way. I've got, for the change in x momentum, I've got 0. The net force from the diagram is my force capital F minus twice the force from any one of those springs. And that has got to be equal to 0. I can divide the delta t from both sides, because delta t is not 0. So I get that the force that I apply is equal to twice the force from a single spring. Now the force from a single spring we can get from the picture. If I look up here, I see there's a single spring. It's stretched to distance L, so Hooke's law would tell me that the magnitude of the force of that spring is equal to the spring constant times how far that spring has been stretched from its equilibrium. From the picture, that's the distance L here, L. So Hooke's law tells me that, momentum principle tells me this, so altogether I get that my force, the force that I'm applying, is equal to twice KL. So I'm just going to arrange it this way. The force that I am applying is equal to some constant times how far the springs have been stretched. So this is exactly what Hooke's law looks like for a spring that has a K effective. That is, and those are K zeros, twice K0. In other words, the spring has gotten twice as stiff if I put them end to end. And that's something that you are probably familiar with if you use resistance bands to do any kind of strength training. One band may not be enough for you to get enough of a workout, but 2 bands pulling together gives you twice the force. 3 bands pulling together gives you 3 times the force. So if I generalize this to 10 springs in parallel, that would give me 10 times the force. The spring constant would go up by a factor of 10. It's a series one that is a little more interesting. So let's take a look now at what's going on in series. So now there is the wall. Here is the first spring. And here's the second spring. And there's where my hand is being attached by the force capital F. So there's my force F. There's the system right there. I'm going to give these springs name. I'm going to call that spring number 1, and that's spring number 2. This entire length is L. So I've used some force, and I've stretched that combination of springs out at distance L. If I look at this junction as a system, and I look at this junction as a system, I do have 2 degrees of freedom here. Each spring can stretch however much it wants to stay in equilibrium. So I'm going to need 2 statements from the momentum principle to make that work. So if I look at this first system, I've got, there's the junction. I've got the magnitude of force 1 pulling backwards. I've got force 2 pulling forwards. And notice my hand here is touching something way over on the other end of the situation. My hand is not touching this junction. So my force capital F does not go there. Nonetheless, that junction is in equilibrium. So what we get is, again, this is the x direction. I get that minus F1 plus F2 is equal to 0, or F1 is equal to F2. Now, in principle, these distances, L1 and L2, could be different. That is, the distances that those 2 springs are stretched, but this equilibrium is going to require that those 2 springs are stretched exactly the same amount, because the force is given by, if again I use Hooke's law for the individual springs, I get K times L1 should be K times L2. The K's are the same, the spring constants are the same, K0, 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 K0. So the spring constants can cancel from both sides, and I get L1 is equal to L2. So that's interesting. That tells me that this distance is capital L divided by 2. That distance is capital L divided by 2. And immediately you can see maybe why you need less of a force to hold it this way. Each spring is not stretched the full distance capital L. It's only stretched half the distance, which would require half the force. So now let's take a look at that system. So now I've got, there's the system. I've got the magnitude of F2 pointing backwards, and I've got my force going forwards. And again, it's in equilibrium, so I've got my force minus F2 is equal to 0. The 0 comes from the fact that the junction is not moving. Its initial momentum is 0, its final momentum is 0. So that I get that my force is only balancing F2. Notice that this net force diagram does not have F1 on it, because F1 is not touching the system that I'm analyzing. You only use the forces that are actually touching the system. So what we have here is 2 systems that link F1, F2, and capital F together. But there's no one system that has them all 3 together. We need 2 sets of the system. Okay, So if I use Hooke's law here for F2, F2 is equal to K times however far the second string is stretched, and that's equal to L over 2, which means K0 divided by 2 times L. And this has got the same form as a single spring. Force is equal to K effective times L, where K effective is equal to 1/2 what any spring by itself would give. And if I put 10 of those springs end for end for end for end, every one of those springs only stretches 1/10 of the way. The overall force goes down by a factor of 10, so you make a very loose spring. So you can skeptic check this if you've ever played with a slinky toy. A slinky toy puts lots of little springs together in series. You can think of one coil as a single spring. You put zillions of these together and you get a very loose spring, so loose in fact that you can hardly even tell that there's a restoring force. That's what happens if you put many springs end for end in series. If you took a bunch of springs and put them side by side, you get something that's stronger. And the systems that you're going to be analyzing in the homework have got arrays of springs, say some number of springs perpendicular along the area of some wire, and then some number of springs parallel. And you figure those out by knowing the shape of the shape of the atoms involved in the wire. The force overall, the force on the wire, should be equal to the spring constant of a single atomic spring. And now I've got some factors here that change that. So if I've got n perpendicular telling me how many of these individual chains of springs I've got, that makes the overall spring stronger. If I divide it by how many springs there are along the edge of the wire, that would be n parallel, that makes the springs weaker and weaker and weaker. And that's how you figure out, so you measure this force on the wire, that's one of the givens. So you know what the total spring constant is times L. Delta L is how far the total spring has been stretched. So you measure the delta L, you measure the force. You can estimate what the n perpendicular and the n parallel is, and that would tell you what is the spring constant for a single spring all by itself. And that's what I got to say.